In the last video, we saw our very first quantum gate, the quantum NOT gate. The quantum NOT gate, though, was sort of classical. It really didn't do all that much beyond what is possible with a classical NOT gate. In this video, we're going to see our first truly quantum gate, the so-called Hadamard gate. All right, what does the Hadamard gate do? Well, like with the NOT gate, we're going to start by explaining what the action is on the computational basis states, and in particular it takes the zero state to the superposition 0 plus 1 over root 2, so the amplitudes for both the 0 and the 1 state are 1 over root 2, and it takes the 1 state to 0 minus 1 over root 2. So it has amplitude 1 over root 2 for the 0 state and minus 1 over root 2 for the 1 state, the output. And much as for the quantum NOT gate, the way the Hadamard gate acts on a superposition is linearly. So it takes alpha 0 plus beta 1 to alpha times the output for the 0 state, 0 plus 1 over root 2, plus beta times 0 minus 1 over root 2. And that's a bit of a mess, so we collect up all the terms for the 0, getting an amplitude of alpha plus beta over root 2 for the 0, and alpha minus beta over root 2 for 1. Okay, that looks like quite a mess. In fact, it is quite a mess. Fortunately, in practice, we're mostly not going to actually need to deal with this. I just wanted to do it to be sort of very explicit. Mostly what we're going to do is we're going to work with the circuit representation or with the matrix representation. So the circuit representation, much as for the NOT gate, is this. So it's a single qubit gate, and we denote it with a H for Hadamard. And so that's the circuit representation, very simple. And like the NOT gate, it also has a representation in the form of a matrix. So let's write that out. I'll tell you what it is, and then we'll just check quickly that it's correct. So this, I claim, is the right matrix describing this action on the quantum state. To check that that's the case, well, we need to check that it gives the right action on the 0 and the 1 state. So let's check on the 0 state. That's H. And then the 0 state is, of course, the 1, 0 column vector. And, well, that just gives us, when we multiply this matrix on that particular vector, it just gives us, in fact, the first column, 1 over root 2, 1, 1, which is indeed the 0 plus 1 over root 2 state. And similarly, if we take this matrix and act it on the 1 state, it's H times this column vector, which is in fact just the second column, 1 over root 2, 1 minus 1, which is 0 minus 1 over root 2. So that tells us that this H matrix does indeed give the right action on the 0 and 1 states, and because matrices act linearly on vectors, it must therefore give the right action on any state, a general state like this one here as well. And if you wish, you can go through and actually explicitly check that. Okay, so that's all very well to describe the Hadamard gate in this particular way, and you'll agree, I hope, that it is truly quantum. It's taking these sort of more or less classical computational basis states and producing as output something which is obviously not actually classical. But you might ask the question, why would we be interested in this kind of a gate? What does the Hadamard gate buy us? And it's a little while before I can give a comprehensive answer to that question, but I can explain in terms of an analogy. And the analogy is this. I want you to imagine that it's many, many thousands of years ago, and here you are, let's say in North Africa, and you want to get from where you are over to Spain, the Iberian Peninsula. And okay, so how are you going to do that? Well, if you don't yet have boats, you kind of have really a tough road ahead of you. What you need to do is go all the way through Africa, up and around and down. But if you build a new device, the boat, which gives you access to an expanded range of locations, you expand the range of states that you can traverse. Actually, you only need to go overland a short way, and then you can go through this new medium over to the Iberian Peninsula, really tremendously cutting down the amount of time required. So what the Hadamard gate and similar gates do is they expand the range of states which it's possible for a computer to be in. And what's important about that is that by doing that kind of expansion, it actually creates the possibility to take shortcuts. Basically, we're moving in a way that's not possible in a conventional classical computer, and maybe that actually lets us do some computations faster. Another similar sort of an analogy is to the game of chess. Imagine that you were playing chess and the rules were changed a little bit in your favor, maybe enabling your, let's say, your rook, an expanded range of moves that is given more flexibility. Well, that might enable you to achieve things like checkmate much faster, because you can get to new positions much more quickly. And the same kind of thing is going on with the Hadamard gate. By expanding the range of states it can access, or the range of dynamics it can generate beyond what's possible in a classical computer, we create the possibility of being able to take similar kinds of shortcuts. Okay, we'll actually see explicit examples later. Just to get sort of a bit more familiar with the Hadamard gate, let's do the analysis of a very simple circuit. So single quantum wire representing a single qubit, and we're going to do two Hadamard gates in a row. What's the effect of this? Actually, it's good to just pause a second and try and guess what you think the result is going to be if you input an arbitrary quantum state. Once you've done that, let's look what happens to the zero state. Well, the first Hadamard gate takes it to the superposition, 0 plus 1 over root 2. And the second Hadamard gate, of course, takes, so we've got over root 2, takes the 0 to 0 plus 1 over root 2, plus the 1 is taken to 0 minus 1 over root 2. And you'll notice that the 1 terms here cancel each other out. So you're just left with the 0 term over root 2 times root 2, but there are 2 of them, so you actually end up with the 0 state. It's not changed, in other words. And the one state, excuse me, is taken to 0 minus 1 over root 2 by the first gate, and then to 0 plus 1 over root 2 minus 0 minus 1 over root 2. So now the 0 terms cancel with each other, and the plus 1 terms reinforce. We've got a double minus here, and we end up with a 1 state as the output. So in fact, this quantum circuit is also equivalent to the quantum wire. Okay, there's an alternate way of seeing this, which I won't actually work through in detail, but again, you see that an arbitrary input psi is taken to the first gate h psi, and then this state is taken to h times h psi, and you can check algebraically that if you take the matrix H and compute it's square, it's just the identity matrix, and that's the reason why this is the quantum wire. Okay, so just a little question to ask. You know that Hadamard gate, the matrix representation, or the Hadamard matrix, as we'll often call it, you might wonder, so let's write it out. You might wonder why there's that funny minus sign down there. Why is that there? Why don't we instead have, let's call it H tilde? Why not just have this? No minus sign. So we'd have H tilde acting on 0, gives you the equal superposition of 0 and 1 over root 2. And similarly for the one state. And actually it's pretty easy to see what the problem is. Imagine that we'd started our quantum circuit and applied the H tilde gate, or this supposed H tilde gate. But imagine that we'd started with the state 0 minus 1 over root 2. That's a perfectly good quantum state. We apply this H tilde to it. So H tilde times 0 minus 1 over root 2. And you see that you get, this is plus, sorry, is 0 plus 1 over root 2 there's a 1 over root 2 factor out the front from here, I forgot to write down. So minus the same thing, 0 plus 1 over root 2. So these terms cancel each other, and we're just left with 0, nothing at all. And remember, I said that the quantum states have to be unit vectors. This is not a properly normalized quantum state. So we see that having this plus 1 down here, changing this sign, somehow actually destroys this property of being a properly normalized quantum state. We start with a properly normalized quantum state, we end with something which isn't. And that's in some sense, or it's closely related to the fact that H tilde is not actually a legitimate quantum gate. We'll explore this fact a little bit more in the videos to come. But H itself actually does have the property that anything which comes in normalized goes out normalized as well. You can check that if you wish, prove it to yourself. We'll prove it in a couple of videos' time. In fact, we'll prove something much more general. In the intervening time, or there's going to be an intervening video where we're going to take a little bit of a digression, and we're going to look at this normalization condition in a little bit more detail, why it's true, what it means, and in particular, we're going to look at what it means to measure the state of a qubit and to extract information from it. And that process of measurement turns out to be intimately connected to the normalization condition and ultimately to understanding more general single qubit quantum gates.